solubility things. Does it dissolve in water? Okay. It's like that commercial. Does it blend? Okay. I thought that was fine. Does it dissolve in water? So to dissolve, we're looking at solubility. What is our rule for solubility? Like dissolves like. Like what dissolves like? Like forces. So step one, what are the forces for each of those molecules? Okay. We have a pre-step one. To get the forces, what do we need to know? The bonds, which we would get from the structure. How do we get the structure? From the name, nomenclature. Water looks like what? H2O. What kind of force would we expect water to exert on another molecule? Hydrogen bonding. Ethanol. 2 carbons and an OH. What kind of force would we expect from ethanol? Hydrogen bonding, because you see the OH. Would we expect water and ethanol to mix? Yes, that's usually why what we celebrate each. Okay, so hydrogen bonding, similar. We would expect them to mix. Chloroform. That one's really irritating because it's a common name. But here's our structure for chloroform. What's our strongest force?
Chlorine to carbon.
Okay. Strongest force, and I heard chlorine to carbon. Chlorine to carbon is a bond, which is what type of bond? Polar covalent, which generates dipole-dipole forces. Is dipole-dipole similar to hydrogen bonding?
Yes.
Yes. So, does it dissolve in water? Ooh, someone hedged their bet on that one. Partially. It's pretty crappy, actually. It doesn't dissolve very well. Okay? We might say, well, why? If we looked at all the forces, because Mike listed out all those forces, whatever day that was, we said ionic, hydrogen bonding, dipole-dipole, and London dispersion. Okay? And if I look at that list, hydrogen bonding is right next to dipole-dipole. Those are similar. Those are arbitrary delineations. That makes it look like there's 4 boxes. There aren't 4 boxes. We have a full spectrum of boxes. We've arbitrarily decided that that bottom spectrum is London dispersion forces. That next section of the spectrum is dipole-dipole. That next section is hydrogen bonding. That next section is ionic. If I look at hydrogen bonding in water, I'm probably somewhere near the top of the hydrogen bonding category. If I look at chloroform, probably somewhere near the bottom of the dipole-dipole category. Are they actually that similar? No. Okay. How do we know that by looking at the structure? That is a very tricky thing. Okay. Mostly that comes from experiment. We come up with a guess, we test that guess, we prove we're wrong, we come up with a new theory. It's not these 4 nice, neat boxes. It's an infinite line of boxes, and they're at opposite ends of those box sections. Okay? Acetone. What do we think? It's the force. Dipole-dipole coming from the name of the carbon-oxygen double bond. The functional group within that structure is a ketone, but I did not ask for the functional group. I asked for the carbon-oxygen double bond. Carbonyl. Okay. If we expand that out to reference the carbons that are attached to it, yes, now we have a ketone. Okay. So what do we think? Dipole-dipole force. Chloroform had a dipole-dipole force, and it was not soluble, right? So acetone. What do we think about acetone? Now you're like, oh, I ain't going to guess. Last time I guessed, I was wrong. Yeah. You will be wrong. It's okay. That's actually why I wrote the question this way.
Would it, as maybe the oxygen might play a part in hydrogen bonding?
So interesting. You're seeing the dipole and saying, Mike's already being tricky, so I'm going to look beyond just the strongest force. Okay? And you're now saying, okay, that oxygen, if I look at how that would interact with water, that force, come on, pen, that force would be what? Hydrogen bonding. So am I really looking at dipole-dipole? No, I'm looking at hydrogen bonding. Is hydrogen bonding similar to hydrogen bonding? Yes. What is this one? Soluble. Good work, Henry. Okay. But just because you did a good job, throw you on the spot with the last one. Diethyl ether. What's our force? Okay, we'll accept dipole-dipole. Okay, which then puts us in, well, maybe it's more like acetone, maybe it's more like chloroform. Henry had a good idea. Let's see what happens if we threw water in there. Can we get a stronger force? What happens if we threw water in there? What would that water interact with? What force is that? Hydrogen bonding. Which would then mean diethyl ether should be soluble in water, and of course, what is it? It's not soluble. Too many hydrocarbons. Okay? Well, what if we just erased one of those?
I think because it's central, it's like surrounded by it. Still.
Okay. If we consider the structural effects, do we have a dipole generated on this? Okay. We have this one moving downwards, okay, and it's a little bit larger with the diethyl ether. What is a special feature, and those of you that have talked to me about the lab know this answer, Anthony. What is a special feature about those bonds and those bonds? What is that feature? They can rotate. So yes, the dipole is aimed downwards, and yes, we should say that should interact with water. But what can very quickly happen? That little ethyl group can swing, 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 whack! Now water can't interact. But if it moves downwards, then what happens to the dipole? Well, then the dipole would be aimed that direction. So, well, but it still has a dipole then that direction. Except then what happens? The other ethyl group goes and whack! So then the dipole is aimed that way. Where's the net dipole? Nowhere. If we have no dipole, can we have hydrogen bonding? If we have no hydrogen bond, well, we have no dipole, so we can't have hydrogen bonding. If we don't have a dipole-dipole force, then it's London dispersion. Is London dispersion similar to hydrogen bonding of water? No. Solubility is inherently a tricky subject. It is not as simple as like dissolves like. Okay? We can scale that to like forces dissolve like forces. Okay? But then we have to remember there's a gradient of those forces. And then we have to remember that there are other contributing factors. Like maybe when we mix things, it's not just what they look like on their own, but when they mix, they create a new force. Maybe we also have to consider that the structure gets in the way. That's a lot of things to consider when we look at solubility. Thankfully, solubility makes such a small part of the class that we aren't all that concerned about all those extra features contributing to our overall understanding of organic chemistry, except all of those features are things that you need to consider when you're looking at organic chemistry. Okay? We have to apply all of that knowledge. Okay? Yes, that's daunting. This is why I said you will have to accept some losses. Pick up the best you can and work within those limitations and move forwards. Okay? Bounce ideas off of other people. What can be done with these? Does salt dissolve in water? Yeah, that's ionic versus hydrogen bonding. We might think, yeah, that shouldn't mix very well. Okay. But when we add salt to water, what do the salt molecules do? They dissociate into the individual ions. So that when I look at salt dissolving in water, it's not a single molecule of water interacting with salt or a chloride ion. It's 6 or 7 of them. Those 6 or 7 ion dipole forces end up being more stable or stronger than the ionic forces in the original salt. If we look at oil, what happens? Well, oil had London dispersion forces from the outset. Water has hydrogen bonding. When I add oil to water, what happens? Separates. They don't mix. Okay, why? Dissimilar forces. Well, salt had a dissimilar force. Can I get water molecules interacting preferentially with oil where I get a bunch of them around it? It's a London dispersion force that's not very strong. Why does salt work? I'm generating a stronger force with that ion. Okay? The charge is generating a stronger attraction. The more charge we have, the more interaction we get. Okay? When looking back at water. So how does soap help water or oil dissolve? What is soap? Amphipathic. Okay, I like that. So we'll describe what soap does. Instead of using a structure, we'll use a new word. Okay, so what does amphipathic mean?
It has one polar side and one non-polar
It has a polar side and a non-polar side. Okay, so we have something like this. Okay. Well, P and NP, that's not very useful. Let's go to structures. 1, 2, 3, 4, 5, 6, 7, 8, 9. I think 9 is the optimal length. When we look at the far right, what do we have? Carbons and hydrogens, effectively oil. We look at the far left, what do we have? Okay. We have what is effectively an ion, or what is an ion, which has a very strong attraction to water, just like salt does. When salt associates in water, what do we make? An ion. So one part of this molecule interacts very strongly with water, one part interacts very strongly with the oil. Okay? So this molecule can bridge that gap and help them kind of talk to each other. But if it can only do it with one molecule at a time at each end, it doesn't really help. What ends up happening? You form what are known as micelles. Okay? Our polar part here being represented by the sphere and the nonpolar part by the tail. The oil gets trapped in with the tails. The polar part on the outside interacts with water. Why does that become relevant? Because this is OChem. We don't ever want to see that again. Can we take a biology class?
It's a cell membrane.
It's the cell membrane. Okay. So if you pushed into biology, you say, oh, there's no organic chemistry there. We have cells because of organic chemistry. Okay. You ignore organic chemistry, we don't exist. That's kind of important. Okay? So it's those scaling up with those interactions and applying outwards. This is massively important when we look at our forces. Kind of, sort of? Okay. So now what we kind of push into is that video that you all watched. Some of you watched it on Play Pause It, and I was looking through and I was like, nobody's watched this. And I remembered I said, yes, you could watch it on YouTube. So those of you that watched it on YouTube, thank you. You're going to go back and watch it on Play Pause It. Should I answer the questions? Yeah. Good. Okay. So the slides that we have set up now, okay, are slightly different from the slides in that video. Okay. The old slides show up with a red title. So what we're going to do is anything with a red title, if you have a question, you ask it. If you don't have a question, I move to the next slide. The issue is that maybe that next slide doesn't have a red title, it has a black title. And guess what happens with the black title? I have a question for you. Okay? So this is your opportunity to make sure you've got the background first before I start throwing softballs at you. They're probably hardballs. Okay. So Our bonds, how do we know we have a bond? We look at a structure. How do we know there's a bond there? A line. What is a line? Electrons. Okay. Where do electrons exist? Orbitals. Okay. So if I look at a line in a molecule, those electrons must exist in orbitals. Are we aware of orbitals yet? We talked about orbitals in your chemistry career. So ignore me. In your chemistry career, have you ever talked about orbitals? What would those orbitals be called? I think someone said it. Atomic orbitals. Okay, right? S, P, D, F. Okay, all those awful things. Okay, you're like, I just hope I never have to see it again. You kind of don't, because we changed it. Okay. What is happening with atomic orbitals? Well, that's where our electrons exist for what?
A period of time.
For atoms. That's where they exist. What happens when I draw a molecule? Do I have an atom anymore? No, what do I have? I have a molecule, which means my atomic orbitals questionably don't exist anymore because I don't have atoms. I have a molecule. Those atoms are now interacting, changing that characteristics, or those characteristics. There are two big theories that come out of how we bridge that, bridge that gap. I thought it was supposed to show up down here at the bottom, two of them. Okay. One is hybridization theory, okay, which, as the video said, was really just a way of doing what? Magic. Yes, it is pretty darn close to that. Okay. The other one is the linear combination of atomic orbitals, molecular orbital theory, okay, which is a fancy way of saying you need a supercomputer. Okay, that's ballpark. Okay. How many of you have a supercomputer? Okay, so let's rely on the hybridization theory. Okay. So we have our atomic orbitals. Do you have a supercomputer? That's not really fair. We have our atomic orbitals, okay, and then we have our molecular orbitals. And they need to match. So the first example we could pick is the example we've been picking a lot of times, methane. When we look at methane, we could draw out its Lewis structure. Right? How many molecular orbitals should we have? Why 4? The lines represent bonds, which represented electrons, and electrons exist in orbitals. So there we go. We need 4 molecular orbitals. Okay? What do we know about those molecular orbitals? Are they different from each other in this molecule? No. So I need 4 identical orbitals. What else do I know about them? Goes back to Vesper. They all push away from each other. So not only are they all equal, but the bond angle between them must be 109.5. Okay, so I know those things to be true because I can see that in my molecule. So I go back and look at the atomic orbitals. Do I have 4 equivalent orbitals? No. Failure number 1. Okay, I needed 109.5 degrees between all of my orbitals. What is the bond angle between 2 p orbitals? 90 degrees. Failure number 2. The atomic orbitals no longer exist. Somehow they had to get mutated. How did they get mutated? Magic. Okay. My wife missed this reference, so I want to check. Mr. Blaine? Okay, one person shook their head yes. Okay, so as long as one person gets it, that's okay. Okay. So hybridization theory, he's funny. Go look at, well, funny. He does magic. Look it up. Okay. We will take the number of orbitals in our hybrid. Okay. Will equal our electron groups. So in methane, we had how many electron groups? 4, which means I need 4 orbitals in the hybrid. Well, how many orbitals do I have? It's greater than 3 and less than 5. There are 4. Okay? Those 4 orbitals conveniently are drawn right here. We have 1s and 3p. Okay, so if I need 4 molecular orbitals, what I'm going to do is take all 4 of my atomic orbitals, I'm going to throw them into my giant magic pot, and with that magic pot, I will then rip out of that magic pot 4 equivalent new orbitals. And I'm going to say, ta-da, this is what they look like. Okay? Ta-da, that's what they look like. where the electron density will be aimed in a primarily one direction. Okay, that direction would be towards the point of what shape? A tetrahedron, because the shape for our 4-electron group molecule is a tetrahedron. Okay? Yes, my drawing sucks because I can't draw orbitals in 3 dimensions. Don't give me too much of a hard time. Okay? What happens if we switch to a new molecule where we had only 3 groups of electrons? Well, 3 groups of electrons means I need 3 orbitals in my hybrid. Okay? Which 3 do I pick? The first 3. Okay? Because I'm tall, I'm going to count from the top. The first 3 I see are p-orbitals. Why would I use the ones that are filled first?
Because they satisfy the one lowest first.
Lowest energy. Okay? Our whole point is to neutralize things, move to the lowest energy. Which orbital will we always use first? S, because lowest energy. So if S is going in and I needed 3, thank you, Manuel. I needed 3 molecular orbitals. Let's do it that way. 3 molecular orbitals, and I've added an S in. I need some more. That's only 1 to 3. That doesn't work. I need to add 2 more orbitals. Those 2 orbitals left are P. And I end up with 3 new hybrid orbitals. What do I want to call those 3 new hybrid orbitals? Jeremiah. Okay. We could go through and call each of those Jeremiah. That's a bit confusing. Okay. So if my parents got together, they could have, instead of named me Michael, they could have named me Joth. Okay. Because my dad's name is John, and my mom's name is Ruth. They just jammed their names together, just kind of like my wife and I did with our last name, to make the new orbital. Okay, why did they not do that? Because they thought Joth sounded weird. Okay, what did scientists do? Well, that didn't sound very weird. Let's just do it anyway. Okay, the names we're using for those hybrid are dependent on what orbitals we put into it. That's why we call them sp2. Each one of those is sp2. What is left over? There's a p orbital that I didn't touch. I can't destroy it. It's still there. Okay, what if I had only 2 groups of electrons?
SP.
I would have sp. What would be left over? 2 p orbitals. Okay, we end up with that picture. Okay, I know I said this would... You guys had questions on this, right? I heard you ask questions and say that's why we kept talking about it, right? Just agree with me, because I said I was going to skip it. Okay, and we ended up talking about it. Here's my question, though. Does anybody notice a difference about the sp orbital versus the sp2 versus the sp3?
SP orbitals on the bottom, horizontal.
So you're saying the sp orbitals at the very bottom here are drawn flat, where those are kind of drawn crooked. Why are they drawn flat? What's the shape for sp? Linear. I decided linear was easier left to right than up to down. That's the only reason. So I don't accept that. That is a difference, but that's not the one we're looking for. Angle, but that comes back to the shape and all that.
Energy level.
What do you mean energy level? Where do you see that?
On the graph.
Yeah, if we look at this graph, I drew this line there. I said, well, why would you draw that line? That's a bit silly. Why would you? That's just ridiculous. Why would you do that? Well, if we look at the sp2s, they're about there. The SPs are like right on it, and the sp3s are somewhere above it. Why would I do that? Because what?
As they hybridize, they pull closer to the p orbitals in energy level.
Okay. I don't like hybridize, but yes. Give me a new word. What am I doing to make those new orbitals? Begins with an A. V, E, A, B, E, R. There it is. We are averaging those orbitals. If I only average 1 p orbital in, Most of it is s orbital, which means the average is going to be halfway in between those. What if I average all 3 p orbitals in? It's going to be closer to the p orbitals, which means those p orbitals will be higher, or those hybrid orbitals will be higher in energy. By a lot? No, but by a significant amount. Yes. Interestingly enough, we'll see that in a little bit. Okay? Hybridization of the central atom. Questions?
I have a question.
Go ahead.
The way that they're drawn larger at one end and smaller, is that just to show that it's a hybrid, or is that showing that there's more?
There's more electron density aimed in that one direction, yes. Okay. So a lot of people look at all the pictures and go, oh my gosh, that's all those pictures. I don't understand what's going on with all those pictures. Let's step back from the pictures and ultimately get at the big idea. You need to be able to identify the hybridization of your atom, okay, which hopefully, there it is. Let's just look at that. Number of orbitals in the hybrid equal the number of electron groups. So step 1, pen, BH3. What does BH3 look like? And as Ming is suggesting, how many electron groups? 3 electron groups. 3 electron groups means how many orbitals need to go in the hybrid? 3 orbitals. What are the 3 orbitals? S and 2 p's, and the hybridization of the central atom is sp2. Why didn't you show me that first? I want you to see where it's coming from. Does that work enough for an answer? Okay. So CO2, what's the hybridization? SP. Okay. Oh, and because this is slightly different slides, in the video you'll notice that I had quotes around the molecular. Why would I have quotes around the molecular? To make a molecule, what do I need?
More than one?
I need atoms, plural. I need at least 2 atoms. Okay. What did I just describe? The hybridization for what? For central what? Atom. Atom versus atoms. Provide the hybridizations for the bonds in BH3 and CO2. I'll give you till 12:15. It's like 2 minutes. What is the hybridization of the boron in BH3? sp2, which means boron's contribution to those bonds is what? So cool, I've now defined the hybridization for boron. Did I define the hybridization for the bond? No, because to have a bond, what do I need? I need at least 2 atoms. Well, I've only defined 1, so let's draw in another. Let's draw in hydrogen. For hydrogen to contribute, it must now also contribute. Over here, I conveniently have the exact same one. So it looks like someone thought about this and said, we're going to make them all the same. I don't know who that person would be. It's clearly not me. I don't think that much. What is the hybridization of the hydrogen's contribution? S. Does it need to hybridize? No. There's no reason to hybridize, so it stays S. So if I look at the bond for boron and hydrogen in BH3, what is it? sp2s. Okay. Officially, I could break it down and say hydrogen, 1s, bonded to boron, sp2. What about that bond? There it is. How many of you just went, like, was it really that easy? Okay. Let's make it worse. And a little bit faster, like that nursery rhyme. Isn't there a nursery rhyme? A little bit faster, a little bit worse? Yeah, that's the only line I remember. So let's describe the bonds now in this guy. What was the hybridization of the carbon? sp and sp, because they're opposite each other. Here's an interesting dilemma. How many electrons could I fit? To a bond, how many do I get? 2. And a bond is represented by a single line. What's the hybridization of that and that? How many sp orbitals would I then have? 4. How many sp orbitals do I have? 2. So those clearly cannot be sp for that second set of lines. What is left over? What was not used? 2 p orbitals. What about the oxygens? I shouldn't have done those in purple. Let's do those in blue. How many electrons groups around, I'm looking at the rightmost oxygen. This one's always fun too. Maybe we missed that in the carbon. How many electron groups around that oxygen? 3. 1, 2, 3. Maybe I said 4, because aren't there 2 lines there? Are those 2 lines in a unique space? No. Which then means they count as 1 group. So I have 3 groups around the oxygen, which means the hybridization is? sp2. So there's an sp2 for that one. There's an sp2 for that one. There's an sp2 for that one. How many sp2s am I allowed to have? 3. How many have I shown? 3. What happened with that last one?
Isn't that in the same group?
Same group. It has to be a different orbital because it's now going into saying there's 4 electrons there. That single line straight across is only 2. Okay, so if I have a second line, I need another orbital for another set of electrons. So what orbital goes for that one? That is our p orbital. Same thing happens on the other side. So if I now want to evaluate the bonds, I have one set of bonds where it's the carbon sp bonded to the oxygen sp2. I have another set that is the carbon p bonded to the oxygen p. There are 2 of the top one, there are 2 of the bottom one because we have 2 different oxygens. Yes, no? I heard a yes. The rest of you may be angry at that person. This is why you should speak up. Okay? So let's take this to a next level. Why on earth do I need to do that? Why do I have to use these p orbitals? And remember, orbitals can only hold 2 electrons, and our orbitals are always located in different space. So when we looked at our s and our p orbitals, the p orbitals, there were 3 of them. You notice that we have one on the x-axis, I can label it x-axis, y-axis, and then z-axis. Why did I not just put them all on the x-axis? They would repel each other. I can't put more than 2 electrons into the exact same space, which begs the question, how did I even get a double bond? Well, what happened when I covered the carbon with the oxygen? I took the hybrid orbitals of the carbon and the oxygen and I overlaid them. So if we were to draw out our picture, our carbon probably looks something like that, and our oxygen looks probably something like this. And there's our overlap. We now have electrons overlapping between those atoms. We have that bond. That's 2 electrons. Where's the second set of electrons? Can it possibly go into that same space? No. How does hybridization theory explain multiple bonds? Are those p orbitals overlapping? You're saying no because I didn't color in a little shape there, right? That shows them overlap. Okay, I accept that. Here's the nasty thing about quantum physics and electrons. What can electrons do? Jump through space where they're not allowed to be. Those p orbitals are close enough to each other that the electron says, I can make that gap. Whoop! It jumps over to the other side, which then means it can overlap. As long as those orbitals are in the same plane, it can make the jump. What happens if I twist out of the plane? It can't make the jump. Okay? So we now have two different types of overlaps. We have an overlap with our SP and our SP2. Okay? That one was an obvious overlap because that was a, people that have talked to me, direct overlap. The p orbitals did not directly overlap, also known as indirectly overlap. Direct and indirect sound too normal, so we invent new terms for it. Everybody freaks out, oh gosh, new terms. Yeah. These new terms are actually not that bad. For the first one, we refer to it as a sigma bond. For the next one, we refer to it as a pi bond. There's no more double, there's no more triple. Okay? That's a load of nonsense. We have sigma and pi. To make a double bond, what do we need? A sigma, there's one. A double needs a second bond. What's the second bond? A pi bond. How do I make a triple? Another pi bond. Okay? I can only ever form one sigma bond because that's the atom space immediately between the atoms. After that, I have to layer on pi bonds and hope that they overlap appropriately. How can I remember this? Pi bonds came from p orbitals. And conveniently, p begins with p, and pi begins with p. Cool, I can remember that. Pi will always involve p orbitals. Sigma, on the other hand, begins with s, which means it will always involve s orbitals. Is sp an s orbital? What do you mean, kind of? Kind of I'll agree with. Yes, I won't. It's a hybrid. It is an S character orbital. Not an S orbital specifically, but S character. It has S orbital as part of it. sp3 orbitals will make what type of bond? Should I say it again? sp3 orbitals make sigma bonds. Sigma. Single is a horrible word. That's a bad word. Go on. Okay. sp2 orbitals make sigma bonds. The p orbital of the third energy level makes pi bonds. Why did I say the third energy level? Just to confuse you. It's still a p orbital. It still makes a pi bond. Okay?
So did you say pi bond is
The p orbitals can only make one bond. How do I get to a triple bond? I need more p orbitals. Without more p orbitals, I can't make more pi bonds. Okay?
So on the structure, if you're naming, I thought I read that you name the first pi bond, and then there's sigma after.
I would name the first bond sigma, and then everything else is pi. You can only have one sigma in a given space. Okay? So we have the birth of sigma and pi, and believe it or not, we even started to drift into the molecular orbital theory when we showed the overlap of those sp orbitals. Okay? So our hybridization. Everybody went through and did this. Okay. Whether or not you did, someone's going to help you out here. What was the percent S character for the carbon in C2H6? Fine, don't help out. What was the percent character, or S character, for a carbon in C2H6? The hybridization is sp3. Okay. I have one s orbital out of a possible 4. 1 divided by 4 gets me 25%. C2H4. Hybridization is percent character. Last one. Cool, we quantified. Everybody wanted to bring in numbers. I said there wasn't any math. I don't count this as math. Okay? Why do I care? What is the difference between an sp3 orbital and an sp orbital? Energy level. Okay? How do we represent our energy level? What is the lowest energy level atomic orbital? The S. How is it different from the second energy level? And don't tell me that it's lower in energy. That's the equivalent of lower in energy. Closer to the nucleus. Is there something that we've talked about so far this semester that addresses the ability of an atom to hold electrons closer to the nucleus? Electronegativity. By looking at the hybridization, what can we say about the carbon in C2H2 in comparison to the carbon in C2H6? It is more electronegative. Okay. So, well, that's not a big deal. If it is more electronegative, what is it doing to the electrons in the bond to the hydrogen? It's pulling them closer. Okay. Relative to C2H6, that carbon is holding those electrons much, much tighter. So effectively, that bond is gone, right? And we would have what charge on the carbon? And we'd have what charge on the hydrogen? Positive. We just defined C2H2 as what kind of a species? That one we haven't talked about, but you've talked about it in Gen Chem. What did it just get rid of? Did it get rid of an electron? What was our result? What did we lose on going from C2H2 to that? We lost a proton. What kind of a species gives up protons? Acids. By evaluating hybridization and electronegativity, what did we just predict? Acid-base reactivity. Okay. That should be like, wow, like clapping, awesome, applause. That's pretty cool. We're using some very basic principles, and we've now predicted that C2H2 should be expected to react with a base, and C2H6 would not react with a base in comparison. That's amazing. Okay. What are we doing for the rest of the semester? Exactly that. Again, and again, and again. Okay? Officially, we have to define what those acids and bases and all that stuff are, but we will be coming back to that. Okay? So let's look for the real kind of atom bomb. Yeah, let's actually look at this one. So our C2H4. Now that was that double bond. We kind of addressed this when we looked at CO2. So when we go through and look at that double bond, one of them is sigma bond, the other one is pi bond. So if we draw out a fancy picture, the P1s are sp2, the purple ones are our sp2, the blue ones would be our p making the pi bond, right? Everybody kind of see that? Okay. What does that mean about the compound? And you might say, well, I don't understand what you mean. Okay. Well, what you need to do is change your viewpoint on the molecule. Sorry. for those watching at home. So, there's the SP2s, right? Right in line with the plane of the board, right? Everybody see that? Perfect. If I were to look at the P's now, what would they do? Now I got the P's, right? Okay. And as long as they're in the proper distance, the electron can hop back and forth. Okay. Right? Hop back and forth, right? What did I just do? What was that action? What did I rotate? I rotated the atom. By rotating the atom, what happened to that overlap? It disappeared. Okay. The instant it disappears, can the electron jump? So we took an electron that now had lots of space, yay, back and forth. And now we said to the electron, no, stop. Okay. Let's do the same thing to you. You can roam wherever you want. Nope, you go to jail. Where are you happier? Free space. Same thing's happening with the electrons, which means the electron contributes to this and says, Mike, you can't rotate. I'm going to try and rotate. This is me trying. And what happens? Ooh. That was also a joke. Nothing rotates. Okay, well, maybe that's consistent for all atoms. Let's go back to our sp2. The sp2s connect, right? Okay, what happens when I rotate? What do you mean, nothing? I'm rotating. The electrons are still overlapping, which means the sigma bonds freely rotate. Anything with a pi bond cannot. This goes back to, everybody goes, well, if hybridization is just magic and we're just making stuff up. Okay, well, I can just make stuff up too. Why hybridization is beautiful is not that we just made stuff up, but that we made stuff up and it worked. Okay? That's what makes this phenomenal. So when we're looking at pi bonds, that means those two structures up there are not the same. Notice the structure on the left. Where are the R groups? They're both on the, whoa, that's close enough. They're both on the bottom part of that pi bond. In the other case, they're on opposite sides. If it was only a sigma bond that connected those two carbons, those structures are identical because I can freely rotate. Because I have a pi bond, I can't do that free rotation. Okay. What does that unfortunately mean? Now that we have different structures and we can tell a difference between them, we now have to name them. What do we choose to name them? Bob and Sally. No. We ended up with cis and trans. Why do we pick cis and trans? Germans. That's why we pick cis and trans. Because Germans were primarily responsible for this. And if we go back to German, cis and trans have roots back to German language. Okay. What does cis mean? On the same side. Never mind, ignore that for the moment. Cis, same side. It's relevant later, but we'll come back to it. Trans, opposite sides. Okay? Cis, same, well now you'll remember cis, and maybe you'll remember the naming later. So if we take a look at the following molecules, would we expect them to show cis-trans isomerism? So the isomerism just means that we have two options. So when I look at these molecules, would I expect them to have cis-trans options? Let's take a look at this last one. Is it in the cis form or the trans form? So cis was on the same side, trans was on the opposite. Sometimes it can be helpful to show the hydrogens. Pen. What would this structure look like if I rotated that bond? The same. So do I have cis-trans? No. If I rotate the bond and it looks like a different structure, then I have cis trans. If I rotate that bond and I can't tell the difference, then no cis trans. Next one. Right to left. Being creative today. Someone laughed at that too. Does that have cis trans? Okay, let's pause for a moment, because maybe what you're looking at, seeing the points, and you're seeing all the carbons, and that's cool, I like that. But let's clarify this, and let's actually say that those are hydrogens. Do we have cis trans? No. If they're carbons, now does it all of a sudden carry cis trans? No. Okay. It's not necessarily tied to hydrogen, it's that do we have distinguishable groups? If we have two groups that are identical on one side of the double bond, no cis trans. These two, whoa, come on, pen. These two groups are indistinguishable. These two groups are indistinguishable. That prevents the cis trans isomerism from happening. How about the next one? I mean, two no's, hopefully we'd get a yes in there somewhere, right? Law of odds. Is there a difference between those carbons? Yeah, one is only connected to one, the other one's connected to two. Those are different, okay, thankfully. But how about the other side? Let's pretend I didn't draw that. What is that chlorine different from? This is where having implied hydrogens can bite you. Okay, if we draw on that hydrogen, we can now clearly see that the chlorine is different from the hydrogen. Yes, we have cis trans. Last one. This one's kind of a curveball. Is hydrogen different than carbon? Is hydrogen different than carbon? Does it have cis trans? Yes, because you're saying if we rotate that, it would look different, right? Okay. So here's a feature for me. I want you to do a little triangle. No, seriously, do a little triangle here. And what I want you to do is rotate it. So take your right hand, and I want you to rotate that triangle without breaking any contact points. Rotate it so that your pinky finger is facing you. Your palm is facing you on your right hand. Don't break any contact. And the other one must be away from you. Please don't break your hand. Can you do it? You're breaking the contact. You're breaking the contact. Yes, you're breaking the contact. Take one through. Interesting. What happens when we have a ring? They're sigma bonds, but you can't rotate. Yes, I have the potential for cis-trans isomerism, but because I'm in a ring, what happens? It can't physically rotate. Ring structures prevent that internal rotation, just like double bonds do. Lost track. Okay? So, atomic to molecular, questions here on this slide. Remember, this was all the stuff that popped up? We called parent A, B. When parent reacted with A, what happened? Increased the amplitude, meaning more probability. Parent reacted with B. Canceled, which means no probability. Okay. So when we looked at sigma bonding, or s orbitals, right? We said they are represented by those waves. I can take those waves and I can overlap them. If they overlap in such a way where they have the same amplitude, what happens? They bond. If they have opposite amplitudes, they don't bond. And the results I get out of this would be 2 molecular orbitals. There are 2 possibilities when I bring atomic orbitals to interact. Okay? I can't ignore one. That is a valid possibility. Okay? So I end up with a bonding orbital and an anti-bonding orbital. The anti-bonding shown with the star. Okay? What type of overlap do I get here? When I take 2 s orbitals and I bring them closer to each other, what overlap do I get? I get direct overlap, also known as what type of bond? Sigma. So instead of calling it bond and antibond, I can call it a sigma bond and a sigma antibond. This generates my molecular orbitals by linearly combining the atomic orbitals. Linearly, on the same line, we took the atomic orbitals and what do we do? They overlapped. Did they overlap well? Lower in energy. Did they overlap poorly? Higher in energy. That's it. I didn't say that's easy, I just said that's it. Does that make sense? Okay. What happens if we move to pi or p orbitals? If we're on the y-axis, right? I think I picked y. Oh, I can't even see the letters on that one. Tried to pick y because that was going to be the easiest to overlap. It didn't quite work. So we're bringing those p orbitals together. Okay, and if we're on the y-axis, when I look at the p orbital, there's that one and there's that one. What type of interaction am I going to get? A sigma interaction. There's a direct overlap between those. That's interesting. It's a p orbital, but I'm getting a sigma interaction. Molecular orbital theory more appropriately deals with proper bonding. Okay? So we end up kind of shifting between molecular and hybridization theory, and we bring in hybrid orbitals to help kind of remove some of that nuance of getting a sigma bond. But when I overlap those, what happens? Okay? Our p orbital has a positive and a negative lobe. What if they interacted in this fashion? Whoops. Those are now in what? Same phase. And being in the same phase, the amplitude increases. So I see an increased probability of finding the electron where the orbitals overlapped. That overlap happens to be where? Between the nuclei, which then means I have a bond. That bond should be drawn lower. It is a sigma bond because it is a direct overlap.
How can they touch like that? Would they repel each other?
So the electrons may repel, but we're not talking about charges here. Those are phases. Okay, so when we look at a wave, we have an up amplitude and a down amplitude. Okay? The positive doesn't repel the positive. We're just adding those two together. If they're both positive, they add. If they're positive and negative, they cancel. Okay, so it's not a repulsion here, which is very, very tricky. That's wave physics and physicists. Kind of my explanation for whenever I don't know. Physicists. Okay. What happens if we look at the px? Where is the px relative to the py? Perpendicular to it. Which means if I drew on the px, what kind of overlap would I get? I'd get an indirect overlap. That's a pi interaction. Okay? What if they interacted like this? Positive, negative. They are in phase, which means they're bonding, which means what type of bond? Pi. What about the PZ? What do you mean same thing?
Same thing, but under 90 degrees rotation.
PZ would be another 90 degrees rotation, which I cannot draw coming in and out of the plane. If we drew them with the same phase, what happens? Bonding. Is it different in energy than the other pi? No, it's identical, which then means 2 pi. What if they weren't in the same phase? They would cancel, and I would end up with anti. Those would be pi antibonding and sigma antibonding. These are now the molecular orbitals. What can I do with molecular orbitals? What can I do with atomic orbitals? Fill them with electrons. What can I do with molecular orbitals? Fill them with electrons. The part of molecular orbital theory that becomes really important that we will evaluate fairly frequently are the pi orbitals. And with that, we really have to be done.